Greetings! My name is Fatma, and I am here with my team members Nicolas, Konstantinos, and Diego to present to you our project. But before that, let us assess the delicate situation that we are in. Currently, we're in the hospital waiting room during the pandemic period, and 10 patients are in a very bad state and still waiting to be taken care of. The problem is that there are only 3 available beds in the ICUs. Let us see how the 2 physicians are going to make a decision on the ICU bed assignments. Arrived just in time. So, as we already discussed, we have 10 patients in the waiting room and 3 unoccupied beds in the ICUs. Our physicians are still having crucial discussions about bed assignments. They both agreed on giving the first bed to patient number 4 and the second one to patient number 9, but they disagree on the last one. The time keeps running and no decision is made. In the meantime, when we look again at some updates in the waiting room, we see that we have 5 new patients and, oh no, a patient died. Time is a very important factor in these situations and every second counts. Then, how should we solve this problem of assigning the last bed if those 2 physicians still are in a big disagreement? Well, the solution is here and we thought about it. Yes, a triage system based on randomness in the medical decision making, which is basically like flipping a coin to decide who is finally going to get the final bed. And this random system, ladies and gentlemen, is our main focus of our project, and we are here to discuss about its effectiveness. So, in order to put this random triage system into practice and to make the bed assignment task fair, we have created ICU, short for Help in ICU, which is a platform that is only accessible to medical staff. Aside from the randomness, we will also proceed to present the other alternative triage criteria, as well as the final simulation, which will provide us with an overview of the various triage results. To start off, we get to the login page, where the medical personnel and staff have to fill the username and password fields. Once it is done, we are directed to the main page, where 2 options are presented for us. Let us start off with the performance triage option, where we get to assign patients to beds depending on how many ICU beds are available. To get the anonymous patients list, we load the data we have from the hospital information system. For data privacy and also for fairness reasons, no one is able to see any information about the patients. The number of unoccupied beds are also given. And just after that, we can select the criterion we want to apply for the bed assignment task. For example here, we are going to choose the random criterion, and we can see the results. Another criterion can be first come, first served, which is only dependent on the waiting time. If you are the first one that came to the waiting room, then you are the first one to be assigned to a bed in the ICU. With the same concept, you have the weighted waiting time. Here, it is about probabilities. The more you have waited in the waiting room, the more probable it is for you to be chosen in the next assignment task, but the probability is not necessarily 1. The last one is the most used one in the hospitals, and that is the short-term acute survival probability. And this is how the bed assignment task is done. Simple and secure. But of course, this is only the surface. I will leave the explanation of the algorithm that we have built to my teammate Diego.
We conducted a simulation study to examine the statistical impact of different selection criteria in ICU triage decision-making. Our investigation considers 4 selection criteria: purely random, first come first serve, random weighted by patient waiting time, and physician estimated short-term acute survival probability. In our simulation, we see a waiting room to the left and an ICU clinic with a user-defined number of beds to the right. New patient arrivals to the waiting room are modeled as a Poisson process with a user-defined arrival rate. Moreover, Patient age is drawn from historical data of COVID-19 patients who required invasive mechanical ventilation, while the initial survival probability of each patient is also sampled from historical data. The survival probability evolves according to an Ornstein-Uhlenbeck process until the patient either expires, signaled by a value of 0, or is discharged, represented by a value of 1. It is important to note that this evolution process is highly dependent on whether the patient is in the waiting room or undergoing treatment. We use a simulation step size of 1 second to reflect the critical nature of ICU triage decision-making. Additionally, we add random delays to simulate delays inherent to hospital operations when a patient dies or a bed becomes available. For example, if the selection criterion is the survival probability as estimated by a physician, the delay for the assignment of a patient to a bed will be proportional to the number of patients in the waiting room. To further reflect real-world conditions, the simulated physicians only have access to a noised version of each patient's true health status. The estimation noise can also be adjusted by the user.
Finally, we can analyze the simulation results. All our results are a 30-day simulation in a hospital with 15 ICU beds. We repeat every simulation 8 times and average the results. The figure is subdivided into 2 kinds of plots. The ones to the left shows how many patients recovered and how many died, and where they died, either in the ICU or in the waiting room. The plot on the right shows the age groups that had the most number of deaths. In this first simulation, we have an arrival rate of 8 patients per day, and we do not consider any kind of extra time that the physician might need for assessing the survival probability of each patient before assigning them to an ICU bed. As we can see in the figure and summarized in the table, the survival probability selection criterion yields the highest percentage of recovered patients. In a second place, only with a difference of 2.2%, follows the random criterion. For this simulation, the only thing we changed with respect to the previous one is that we now consider an extra assignment delay in case the physicians take the survival probability as selection criterion. We do it in such a way that for every patient in the waiting room, the physicians need an extra 30 seconds to assess the survival probability and decide which patient will get assigned to which ICU bed. For example, if there are 30 patients in the waiting room, this selection process will further be delayed by 15 minutes. We can see that the survival probability criterion still has the best results in terms of percentage of recovered patients. However, the gap between the random criterion and the survival probability criterion has gotten smaller. Before it was 2.2%, now it is 0.7%. Once again, the other 2 criteria show a poorer performance. For this simulation, we again consider this extra assignment delay. Furthermore, we decreased the daily arrival rate, with 6 patients arriving to the waiting room each day. In this case, a random selection criterion yields the highest percentage of recovered patients, followed by survival probability. The 2 other criteria are once again outperformed. Now, we want to observe how many hours on average the patients have waited in the waiting room, depending on their age groups. For the first simulation, we can see that the patients have made it out alive, most likely because they were transferred to the ICU, lasted longer than the patients who died in there. This is the case for all criteria. This second simulation only changed the fact that now an extra assignment delay is considered for the survival probability. It is interesting to see that even though the parameters are the same, the waiting time for the random criterion is different. One possible explanation for this phenomenon could be that the average waiting time of patients in the waiting room is unpredictable when we are considering a random selection process. The plots of the 2 selection processes that do not consider randomness, which are short-term acute survival probability and first come first served, look more alike to the previous simulation. For this last simulation, where we consider a daily arrival rate of 6 patients per day instead of 8, we see one more time that for random criterion, the behavior changes. Once again, a possible explanation for this is the unpredictability of random process. The other two criterion behave the same. In conclusion, we observed that when applying an extra assignment delay for the short-term acute survival probability selection criterion, the percentage gap between the said criterion and the random one gets smaller. Furthermore, for a system with a lower daily arrival rate, which corresponds to a hospital with less patients, the random criterion outperforms the survival probability criterion. For this reason, one could argue that using randomness as selection criterion has a similar performance as short-term acute survival probability. Lastly, we can clearly notice from all our results that the random weighted waiting time is mostly outperformed by other criteria. So this is it. I hope you enjoyed our project and thank you very much for your attention. Now we would be glad to discuss this with you and answer your question.